Hi everyone, it's Professor Plimpton, and today we're going to talk about triple integrals in spherical coordinates. So in the previous video, we talked about how to evaluate a triple integral by changing from rectangular to cylindrical coordinates. In this video, we're going to talk about how to evaluate a triple integral by changing from rectangular coordinates to spherical coordinates. So let's review spherical coordinates. In three-dimensional space, the spherical coordinate system represents a point, rho, theta, phi, where rho is representing the distance from the origin. The angle theta is a polar angle from the positive x-axis to the projection of the point P into the xy plane, where the original point P is x, y, z, and angle phi is measured from the positive z-axis to the line segment OP. So you have point P represented in rectangular coordinates as x, y, z. The same point can be represented using spherical coordinates as rho, theta, phi, where rho is the distance from the origin to the point P. Angle theta is measured from the positive x-axis to the ray OP prime. P prime is the point x, y, 0, which will also be P prime r cosine theta, r sine theta, 0, because x is equal to r cosine theta and y is equal to r sine theta. When you have the point projecting to the xy plane, you have polar coordinates. That's this angle theta. It's the same angle theta as in cylindrical coordinates. And then the angle phi is the angle from the positive z-axis to the ray OP. So remember, we converted from rectangular coordinates to spherical coordinates using the following formulas. X is equal to rho times sine phi times cosine theta. Y is equal to rho times sine phi times sine theta. And then z is equal to rho times cosine phi. In the spherical coordinate system, the counterpart to the rectangular box is a spherical wedge, and it consists of the points E of the form rho, theta, phi, where rho is between values A and B. Remember, rho is representing the distance, so the distance between values A and B. The angle theta is between angles alpha and beta, and then the values for phi are between C and D, and C and D are representing angles. Notice that A will be greater than or equal to 0, because the distance from the origin to the point P will be greater than or equal to 0 in three-dimensional space. And the way that theta is defined, it was always between 0 and 2 pi. If you take beta subtract alpha, that will give you an angle that's between 0 and 2 pi. So a spherical wedge, this solid that we're going to integrate over, it's called the volume element in spherical coordinates. The differential for volume, dV, is equal to rho squared times sine phi, and then you integrate with respect to rho, then phi, and then theta, which is the volume of this representative spherical wedge. Although we define triple integrals by dividing solids into small rectangular boxes, we could have divided the solid into small spherical wedges. So if we take this solid E and we divide it into smaller spherical wedges, E sub ijk, by means of equally spaced spheres, half planes, and half cones. So remember the equation rho equals rho sub I, that's the equation of a sphere in spherical coordinates. The distance is a fixed distance from the origin for a sphere centered at the origin. The half plane, theta is equal to theta sub j. So the half plane is where you have an angle that's fixed. It'll be a constant. And a half cone is where you have phi is equal to a fixed angle phi sub k. So the dimensions of this smaller spherical wedge, E sub ijk, is approximately a rectangular box with dimensions delta rho. Then you have rho sub I times delta phi as the arc of a circle with radius rho sub I, and angle delta phi. And then you also have rho sub I times sine phi sub k times delta theta. That represents a circle with radius rho sub I times sine of phi sub k and an angle delta theta. So this will give us an approximation for the volume of this spherical wedge, E sub ijk. It's given as delta rho times rho sub I times delta phi times rho sub I times sine of phi sub k times delta theta. And so if you multiply these three expressions together, you'll get the differential for volume for spherical coordinates. It's rho sub I squared times sine of phi sub k times delta rho times delta theta times delta phi. So a typical triple Riemann sum will become a triple integral in spherical coordinates according to the following definition. So the definition for triple integral using spherical coordinates is as follows. You have a function f of x, y, z. It has to be a continuous function over this spherical wedge E. Then we can convert to a triple integral from rectangular to spherical coordinates by writing x is equal to rho times sine phi times cosine theta, y is equal to rho times sine phi times sine theta, and then z is equal to rho times cosine phi. And we're going to have to find out what are the limits of integration for rho, theta, and phi. And we also need to replace the differential dv with the expression rho squared times sine phi, and then it will become d rho, d theta, and then d phi. So this is what's called the Jacobian, rho squared times sine phi, Whenever you convert from rectangular to spherical coordinates, you pick up an extra factor of rho squared times sine phi. Therefore, the triple integral over the spherical wedge E of the integrand f of x comma y comma z, and you differentiate with respect to volume, or v, it becomes a triple iterated integral. You have the outside integral corresponding to values for phi, so that's between phi equals c and phi equals d. The middle integral corresponds to values for theta, theta equals alpha and theta equals beta. Your inside integral corresponds to values for rho, so this is between values rho equals a and rho equals b. Your integrand was originally in terms of rectangular coordinates, which means you have to replace the x, y, and z to be in terms of spherical coordinates. You use the substitutions for x, y, and z, so it'll be f of rho times sine phi cosine theta, comma, the y becomes rho sine phi sine theta, and then the z coordinate becomes rho cosine phi. And then whenever you change from rectangular coordinates to spherical coordinates, the differential dv becomes rho squared sine phi, that's the Jacobian, and then you integrate with respect to rho first, theta, and then phi would be last. This is where the spherical wedge represents this E. The E is consisting of points, rho, theta, phi, where rho is between A and B, theta is between alpha and beta, and then phi is between the values C and D. So you have to find out what the limits of integration are, so I'll help you figure out what's the triple iterated integral. What do the values for rho consist between? Well, you're calculating distance from the origin. So you want to find out what's the shortest distance from the origin. That would be rho equals A. The farthest distance from the origin for the spherical wedge, that will be rho equals B. You want to find out what do the values of theta range between. So theta will be between two angles. You'll have an alpha and a beta. So the spherical wedge will start at a value theta equals alpha, and it will end at a value theta equals beta. And then phi measures the angle from the positive x-axis to the line segment from the origin to the spherical wedge. And so you want to find out what do the values for phi range between. It'll be between two values, C and D. So note, it's worthwhile to use the differential dv is equal to rho squared sine phi, and then you integrate with respect to rho, then theta, then phi, whenever your solid can be easily described using spherical coordinates, or whenever your integrand, f of x comma y comma z, it contains the expression which we would relate to a sphere, x squared plus y squared plus z squared. So if the integrand contains this expression, x squared plus y squared plus z squared, it's a good sign that we should convert to spherical coordinates. Other cases where you would want to use spherical coordinates would involve if the region contains a part of a cone or also part of a sphere. And as with multiple integrals that we've already talked about, all the properties that we've had for double integrals and triple integrals are also true for spherical coordinates. So let's try out example 4, integrating over a solid in spherical coordinates. Evaluate the triple integral, which is a triple integral over b of the integrand e to the power x squared plus y squared plus z squared in parentheses, all to the 3/2 power. And we're differentiating with respect to v, which represents volume. This region that we're integrating over is b. It consists of points rho, theta, phi. Rho is between values 0 and 1, theta is between values 0 and 2 pi, and phi is between 0 and pi. We're going to convert this integral from rectangular coordinates into an equivalent integral using spherical coordinates to find its value. So notice in the integrand, you have x squared plus y squared plus z squared in the exponent of base e. That's a good sign that we should use spherical coordinates. And this region that we're integrating over is already being described in terms of spherical coordinates. So let's take x squared plus y squared plus z squared, and we'll convert to spherical coordinates. X squared plus y squared plus z squared was equal to rho squared. And then anytime that we have an x, we'll have to have x replaced with rho sine phi cosine theta. Y is equal to rho sine phi sine theta, and then z is equal to rho times cosine phi. So that means the integrand f of x comma y comma z, which was e to the power quantity x squared plus y squared plus z squared raised to the 3/2 power, it's a continuous function over this rectangular box, which is described using spherical coordinates. We'll change this function to be e to the rho squared to the 3/2 power. That will simplify to become e to the rho cubed power. So our triple integral over this region B for the original integrand will become a triple iterated integral. We will integrate with respect to rho first, so that will be your inside integral. Your middle integral will correspond to values for theta, and then your outside integral will correspond to values for phi. Whenever you convert from rectangular coordinates to spherical coordinates, you pick up the Jacobian, the extra factor, rho squared times sine phi. And when you simplify the integrand, it'll become e to the rho cubed, and then you'll also have rho squared times sine phi as your integrand in terms of spherical coordinates. Now let's find out the limits of integration for each of these variables in spherical coordinates. They give us the region. Rho is between 0 and 1, so that corresponds to the limits of integration for your inside integral. The values for theta is corresponding to the middle integral, so 0 to 2 pi. And then phi is for the outside integral, its values between 0 and pi. So you have the triple integral, 0 to pi, 0 to 2 pi, and then 0 to 1 of e to the rho cubed power rho squared times sine phi. That's what we need to integrate and find out the value for. So you integrate with respect to rho first. Notice that you will have to use u substitution. You'll have u is equal to rho to the third power, and then the derivative of u with respect to rho will become 3 rho squared. One thing that we can do is notice that sine phi does not depend on rho. So sine of phi is considered a constant, and we can just factor out sine phi. We cannot factor out sine phi from all three integrals because the last integral, the outside integral, corresponds to values for phi. We can have an integral from 0 to 1 of rho squared times e to the rho cubed. We'll have to integrate with respect to rho for that integral. And then the outside two integrals will correspond to values for theta from 0 to 2 pi and then phi between 0 and pi for the integrand sine phi. Now focus on the two outside integrals. Notice that sine phi does not depend on values for theta, so you can factor out sine phi from that integral between 0 and 2 pi. And so you have an integral from 0 to pi of sine of phi with respect to phi times an integral from 0 to 2 pi of just the integrand 1, and you integrate with respect to theta, and then you have an integral that corresponds to values for rho between 0 and 1 of rho squared times e to the rho cubed power. So you can integrate with respect to rho, phi, and theta all separately because the function, the integrand, can be broken up into a product of a function of rho, of a function theta, and a function phi. So the antiderivative of sine of phi is negative cosine phi. We evaluate this antiderivative between the values for phi between 0 for the lower limit and phi equals pi for the upper limit of integration. The antiderivative of 1 with respect to theta is just theta, and then evaluate at the lower limit, theta equals 0, and theta equals the upper limit, theta equals 2 pi. And then the antiderivative of rho squared times e to the rho cubed power becomes 1/3 e to the rho cubed power after you use u substitution to find the antiderivative. Evaluate from rho equals 0, the lower limit, and rho equals 1, the upper limit of integration. So now you can use the fundamental theorem of calculus for each of those three separate integrals. Whenever you substitute in phi equals pi, you'll have negative cosine of pi plus cosine of 0 when you substitute in phi equals 0. That will simplify to become the opposite of negative 1 plus 1, which will just be 2. Your middle integral was just theta, so if you substitute in 2 pi and then theta equals 0, you would just get 2 pi minus 0, so that just simplifies to be 2 pi. And then the last integral, when you integrate whenever rho is equal to 1, you'll have 1/3 e to the 1 cubed power, which will just simplify to be 1/3 e to the first power, minus when you substitute in 0, you'll have 1/3 e to the 0 power. So you'll have 2 times 2 pi for the first two integrals, and then the last integral will give you 1/3 e minus 1/3, and so this will simplify to become 4 pi thirds times the quantity e subtract 1. That's the value of the original triple integral where we were integrating over this spherical wedge b, and we converted to spherical coordinates in terms of rho, phi, and theta. We'll try another problem. Example 5, setting up a triple integral using spherical coordinates. We're going to set up the triple integral, but not evaluate using spherical coordinates. Set up an integral to find the volume of the region bounded below by the cone z equals the square root of 3 times the quantity x squared plus y squared, and then the region is also bounded above by a hemisphere z equals the square root of 4 subtract x squared subtract y squared. Do not evaluate the spherical integral. Notice that you have an upper hemisphere, so the region was bounded above by an upper hemisphere, z equals square root 4 minus x squared minus y squared. We can convert this easily to spherical coordinates because it represents the upper part of a sphere. So if you square both sides of this equation, you'll have z squared is equal to 4 subtract x squared subtract y squared. If you have all the variables terms on the same side of the equation, you'll have x squared plus y squared plus z squared is equal to positive 4, which means that the left side of the equation using spherical coordinates becomes rho squared equals 4, which simply becomes rho equals 2. So that would be a sphere of radius 2 centered at the origin. We're only considering the upper half of the sphere though. And then the cone, which was the equation z equals square root 3 times the quantity x squared plus y squared, we're going to convert the cone to be an equation in terms of spherical coordinates. So z becomes rho times cosine phi, and then the right side of the equation will become square root of 3, and then square root of x squared plus y squared. Well, I'm going to rewrite this so you have a 1/2 power on the outside. The x squared becomes rho squared sine squared phi times cosine squared theta, plus the y squared becomes rho squared sine squared phi times sine squared theta. That's all inside a square root, or raised to the 1/2 power. Notice that inside the square root, you have rho squared sine squared phi in common, so that can be factored out from both terms inside the square root. So it's phi squared sine squared phi. What would be left over would be cosine squared theta plus sine squared theta. which is the Pythagorean identity, which simplifies to 1. Sine squared theta plus cosine squared theta is equal to 1. So on the left side of the equation, you'll have rho times cosine phi. On the right side of the equation, you'll have square root of 3 times rho squared sine squared phi times 1 after you use the identity, and that'll be inside of square root. Well, the right side, everything that's inside the square root is a square power. So they'll undo each other, and so you'll have square root of 3 times rho times sine phi on the right side of the equation. We're trying to find out what's the equation using spherical coordinates for this cone. Let's divide both sides by rho cosine phi so we can have all the variables on one side of the equation. And then we'll also divide by square root of 3 to the left side of the equation. So on one side of the equation, you'll have rho sine phi divided by rho cosine phi. Well, that will simplify to just be tangent phi. And then the other side of the equation, you'll have 1 divided by square root of 3. So now solve for the angle for phi. Use the inverse tangent function, or arctan. Take inverse tangent on both sides of the equation. That will give you just phi is equal to inverse tangent of 1 divided by square root of 3, which is the angle pi divided by 6. So for this cone, z equals square root 3 times the quantity x squared plus y squared. Another way of writing this equation from rectangular coordinates would be the spherical equation phi equals pi divided by 6. It's much easier to describe a cone using spherical coordinates because the angle phi is a fixed constant pi divided by 6. So now we're able to set up our triple integral that would find the volume of this region bounded below by the cone and bounded above by the sphere, the upper hemisphere. You have volume would be equal to, you have a triple iterated integral. Your integrand would be rho squared sine phi because that's the Jacobian when you convert to spherical coordinates from rectangular coordinates. You integrate with respect to rho first. Rho was corresponding between values between 0 and rho equals 2. So integral will be 0 to 2 for the values for rho. Phi is the middle integral. Those were corresponding to values between 0, and then we found out the cone was phi equals pi over 6. So the region would be between phi equals 0 and pi over 6. We want the entire region bounded below by the cone and above by the sphere. So we want theta to go between the values 0 and 2 pi. That would correspond to the values on the outside integral. So this integral would find the volume of the region bounded below by the cone, z equals square root 3 times the quantity x squared plus y squared, and then also above by the hemisphere, z equals square root 4 minus x squared minus y squared. We'll try another problem where we have to consider different orders of integration using spherical coordinates. So example 6, setting up a triple integral using spherical coordinates. Let E be the region bounded below by the cone, z equals square root x squared plus y squared, and it's bounded above by the sphere, x squared plus y squared plus z squared is equal to z. So we're talking about this region. It's bounded below by the cone, and it's bounded above by the sphere. So it's this part that we're trying to integrate over. We need to set up a triple integral using spherical coordinates to find the volume of the region using the following orders of integration. But we're not going to evaluate the spherical integral. We're just going to set up the spherical integral in each case. So number 1, we're going to integrate in the order d rho, then d phi, then d theta. So notice that we can relate the sphere, which was x squared plus y squared plus z squared equals z. We can relate this back into spherical coordinates as follows. The left side of the equation is x squared plus y squared plus z squared. Well, that's rho squared in spherical coordinates. And then z is equal to rho times cosine phi. If you take both sides of this equation and divide by rho, then you'll have rho is equal to cosine phi. The sphere was forming the upper boundary of the region, so this will be the upper surface. Rho equals cosine phi. The cone was forming the lower surface of the region that we're integrating over. So z equals square root x squared plus y squared. A cone is easily represented using spherical coordinates. So we'll square both sides of the equation. So you'll get x squared plus y squared is equal to z squared. Change all the x's to be in terms of spherical coordinates and the y's and also for the z's. The x is equal to rho sine phi cosine theta. So you'll have x squared becomes rho squared sine squared phi cosine squared theta. And then plus the y is equal to rho sine phi sine theta. So y squared becomes rho squared sine squared phi times sine squared theta. And then the right side of the equation, z is equal to rho cosine phi. So that means z squared is rho squared cosine squared phi. We've seen this similar idea before in a previous problem. Notice the left side of the equation, you have rho squared sine squared phi in common, so that can be factored out from both terms on the left side of the equation. And then you'll have cosine squared theta plus sine squared theta remaining, which is the Pythagorean identity that's equal to 1. So the left side of the equation becomes rho squared sine squared phi times 1, which will just give you rho squared times sine squared phi. The right side of the equation is rho squared cosine squared phi. Divide both sides of the equation by rho squared, and you'll get sine squared phi is equal to cosine squared phi. Well, take the square root on both sides of the equation. That will give you sine of phi is equal to cosine of phi. The only angle that would satisfy sine of phi is equal to cosine of phi between the values 0 and pi, because that was the restriction using spherical coordinates. The angle phi must be between 0 and pi. The only angle that satisfies this equation would be phi equals pi divided by 4. So that's the cone. Z equals square root x squared plus y squared is the equation phi equals pi divided by 4 in spherical coordinates. So now we can set up our triple iterated integral using spherical coordinates. The volume is equal to the outside integral corresponds to values for theta. Theta will go between 0 and 2 pi because we want the entire region that was bounded above by the sphere and below by the cone. Middle integral corresponds to values for phi. We found out the cone was equal to phi equals pi divided by 4. So the values for phi will go between 0 and pi divided by 4. And then the inside integral corresponds to surfaces. Those were rho values. So rho was going between 0 and then the upper surface, which was the sphere, and the sphere was rho equals cosine phi. Remember that when you use spherical coordinates, the integrand, the Jacobian is rho squared times sine phi. So the triple integral that we need is 0 to 2 pi for theta, 0 to pi over 4 for phi, rho is between 0 and cosine phi, and then the integrand is rho squared times sine phi. This will calculate the volume for the region that's bounded above by the sphere, x squared plus y squared plus z squared equals z, and bounded below by the cone, z equals square root of x squared plus y squared, using spherical coordinates. So number 2, this time we want to integrate with respect to phi first, then integrate with respect to rho second, and then integrate with respect to theta last. So from our previous work, notice that rho was between the values 0 and the upper surface cosine phi, phi was between the values 0 and the angle pi divided by 4, and theta was between 0 and 2 pi. If we're going to integrate with respect to phi first, we need to have the surfaces in terms of values for phi. So let's take this second inequality and find out what does that tell us about rho. So if the angle phi is between 0 and pi divided by 4, that means that rho is between 0 and square root of 2 divided by 2, using that rho is equal to cosine phi is the upper surface. You'll have cosine of pi divided by 4, which is square root of 2 divided by 2. So rho is between 0 and square root of 2 divided by 2 whenever phi is between 0 and pi divided by 4. And then also, if rho is between square root of 2 divided by 2 and 1, angle phi is between 0 and the upper surface, phi equals inverse cosine of rho. So you'll take inverse cosine to get phi by itself, and you'll have inverse cosine of rho. So in other words, if you have rho is equal to cosine phi, and phi is pi divided by 4, this will lead you to say that rho is equal to cosine of pi divided by 4, which is rho equals square root 2 divided by 2. In other words, the sphere and the cone will intersect at the point when phi is pi divided by 4 and rho is square root 2 divided by 2. So this was the triple integral that we set up before, using the integration order rho first, then you integrate with respect to phi second, and you integrate with respect to theta last. We're going to need two triple integrals using spherical coordinates because the values for phi range between two different surfaces, 0 and pi over 4, and then also 0 and inverse cosine of rho. So one triple integral will be as follows. If you want to integrate with respect to phi first, then phi will range between 0 and the surface. Phi equals inverse cosine of rho. The integrand is rho squared sine phi because we're integrating using spherical coordinates. And then you integrate with respect to rho second. The middle integral corresponds to values for rho. Well, rho was between square root 2 divided by 2 and 1, so that's your limits of integration. The lower limit is square root 2 divided by 2, and then the upper limit of integration is rho equals 1 for the middle integral. And then your outside integral corresponds to values for theta. Well, theta was still the outside integral originally, so it's 0 to 2 pi. So that's one triple integral. We also have to add the value of another triple integral where phi goes between 0 and pi divided by 4. So you'll have another triple integral where the integrand is rho squared sine phi. You integrate with respect to phi first. Well, phi goes between 0 and pi divided by 4. Whenever the middle integral stands for the values for rho, rho is between the values 0 and square root 2 divided by 2. So that's the middle integral. It'll be from rho equals 0 to rho equals square root 2 divided by 2. And then the outside integral, again, corresponds to values for theta. Theta is going between 0 and 2 pi. So the sum of these two triple integrals using spherical coordinates is equal to the original integral that we found in problem number 1, using spherical coordinates to set up a triple integral where the integration order was rho first, phi second, and then theta was last. If you have the integration order phi first, rho second, and theta last, we had to set up two triple integrals and then add the answers together to find the volume. So let's finish up this video by talking about how to convert a triple integral in rectangular coordinates to an equivalent integral using spherical coordinates. So example 7, converting from rectangular to spherical coordinates. Convert the following integral from rectangular coordinates to an equivalent integral using spherical coordinates. Do not evaluate the spherical integral. So problem number 2, you have the triple integral, which are values on y on the outside. So it's y equals 0 to y equals 3. You have the middle integral correspond to values for x. So it's x equals 0 to x equals square root 9 subtract y squared. And then the inside integral corresponds to the values for z. It's between z equals square root x squared plus y squared, that's the lower limit, and then z equals square root 18 minus x squared minus y squared, that's the upper limit. Your integrand is x squared plus y squared plus z squared. Notice that the integrand, x squared plus y squared plus z squared, can be easily changed to be in terms of spherical coordinates. So that's what we're going to do. We're going to find out a triple integral using spherical coordinates that will give us the same value as this triple integral involving rectangular coordinates. When we convert the integrand, x squared plus y squared plus z squared, to be in terms of spherical coordinates, that will become rho squared. When we convert to spherical coordinates, we also pick up the Jacobian in the integrand. So the integrand would be rho squared times the Jacobian rho squared times sine phi. And now we're going to integrate with respect to rho first, then integrate with respect to phi, and then integrate with respect to theta last. So we need to find out what are the limits of integration for each of the variables in spherical coordinates. Let's take the upper surface. This is z equals square root 18 minus x squared minus y squared. Let's find out what's that equation in terms of spherical coordinates. So remember, the conversion from rectangular to spherical coordinates were as follows. X equals rho times sine phi times cosine theta. Y is equal to rho times sine phi sine theta. And then z equals rho times cosine phi. That means the equation z equals square root 18 minus x squared minus y squared. After you square both sides of the equation, you'll have z squared is equal to 18 subtract x squared subtract y squared. If you add x squared and add y squared to both sides of the equation, you'll have x squared plus y squared plus z squared on the left side of the equation. So that becomes rho squared in spherical coordinates. And the right side of the equation will just be 18. If you solve this equation for rho, that gives you rho is equal to square root of 18, which is 3 times square root of 2. And then the lower surface, which was z equals square root x squared plus y squared. Well, we've seen this a couple times already. Z equals square root x squared plus y squared. Square both sides of the equation. You'll have z squared is equal to x squared plus y squared. Change z, x, and y to be in terms of spherical coordinates, and then simplify. That will give you the angle phi is equal to pi divided by 4 for this equation of a cone. We have the values for rho. Rho is equal to 3 times square root 2. We have the value for phi, which was pi divided by 4. But now we need to find out what are the values for theta that represents this region that we're integrating over after you project the region into the xy plane, because we originally were integrating with respect to z first. That's a projection of the solid into the xy plane. So your outside two integrals are describing a region after the projection into the xy plane. Your x values correspond to the middle integral, so that's x equals square root 9 minus y squared. That's the right half of a circle of radius 3. So it's x equals square root 9 minus y squared. And then your lower limit of integration is x equals 0. That's the y-axis. Your outside integral corresponds to y values for the original integral, so the y values go between 0 and 3. So we're only integrating between y equals 0 and y equals 3. That's from the x-axis to the value y equals 3. So we're only integrating over the region that's in quadrant 1 in the xy plane. So now let's set up the triple integral using spherical coordinates. Notice that the values for theta only go between 0 and pi divided by 2, because we're integrating only in quadrant 1. So your outside integral corresponds to values for theta. Theta goes between 0 and pi divided by 2. The middle integral corresponds to values for phi. Well, phi is going between 0 and pi divided by 4. And then the inside integral corresponds to values for rho. Rho is going between 0 and then also 3 times square root of 2. That's the upper limit of integration. The integrand was x squared plus y squared plus z squared. That becomes rho squared. And then when we convert from rectangular coordinates to spherical coordinates, we also have to multiply by the Jacobian, rho squared times sine phi. And so the integrand becomes rho to the fourth times sine of phi. And then the integral is theta values between 0 and pi over 2, phi values between 0 and pi over 4, and then rho between 0 and 3 times square root of 2. The value of this triple integral using spherical coordinates will give you the same value as the value of this triple integral using rectangular coordinates. So this finishes our video on triple integrals in spherical coordinates. We talked about how to evaluate a triple integral by changing from rectangular coordinates to spherical coordinates. If you have any questions about any of the examples in this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you in the next video when we talk about vector fields.